Imagine staring at the night sky, every star twinkling in what seems like eternal stillness, only to realize the universe itself is not behaving as we thought. For decades, scientists believed that dark energy, the mysterious force driving the expansion of the cosmos, was constant, steady, and predictable. But what if that assumption is wrong? What if the very force shaping the fate of all galaxies, stars, and planets is shifting, fluctuating, and rewriting the ultimate destiny of the universe itself? Recent discoveries suggest that dark energy is not the immutable cosmic glue we imagined. It's changing, and that revelation could alter everything we know about the cosmos, from how galaxies evolve to whether the universe will end in a gentle freeze or a cataclysmic tear. Today we're diving into 3 shocking truths about dark energy that are challenging the foundations of modern physics. Dark energy is dynamic, not constant. For nearly a century, cosmologists and astrophysicists have worked under a profound but deceptively simple assumption that dark energy, the mysterious force driving the accelerated expansion of the universe, is constant. Ever since the late 1990s, when astronomers first discovered that galaxies were not just moving apart, but accelerating in their recession from one another, dark energy was conceptualized as a uniform, unchanging force, a steady, invisible push against the gravitational pull of matter. This idea was comforting. It allowed physicists to construct models of the cosmos with a sense of stability and predictability. Calculations could be made with precision. Predictions about the distant future of the universe, billions and even trillions of years ahead, could be made with a degree of certainty. At that time, the introduction of dark energy into Einstein's equations felt like a triumph. It filled the gap in our understanding. Without it, the universe's acceleration would have defied explanation. The term cosmological constant was used to describe this force, a fixed number that neatly counteracted gravity's slowing influence. Scientists could, in principle, calculate the fate of everything, from stars and planets to galaxies themselves, based on the assumption that dark energy would remain exactly as it was, unchanged across the eons. But science is never static, and neither is our universe. In recent years, high-precision astronomical measurements have begun to tell a story that challenges this foundational assumption. Observations from powerful telescopes, detailed supernova surveys, and measurements of the cosmic microwave background, the faint afterglow of the Big Bang, have revealed anomalies that cannot be easily reconciled with a simple, constant, dark energy. Some distant galaxies appear to be moving faster than predicted, while others are lagging behind expected velocities. These differences may seem minuscule on a human scale. After all, the distances involved are measured in billions of light years. But in cosmic terms, even slight variations can reveal entirely new physics and forces at work. The emerging evidence suggests that dark energy may not be a constant, unchanging quantity at all. Instead, it may fluctuate over time and possibly even vary across space. This implies that the universe is governed not by a single, predictable force, but by one that evolves, a dynamic energy field, shifting in strength and influence as the cosmos ages. To imagine the implications, consider for a moment that the rules of reality themselves, the forces shaping the universe on the largest scales, may be in flux. Every calculation, every projection about the history and future of the cosmos could require re-evaluation. Physicists are now exploring a new class of models known collectively as dynamic dark energy. In these models, the strength of dark energy changes over time, influencing the expansion rate of the universe in subtle but significant ways. Some theories suggest that dark energy could gradually weaken. If that were the case, the current era of accelerated expansion might slow, eventually giving gravity a chance to reclaim dominance over the cosmos. In this scenario, the universe could experience a cosmic deceleration, with galaxy clusters drawing closer together over unimaginable timescales. Stars might collide or merge, galactic orbits could shift, and the large-scale structure of the cosmos might change dramatically. Other models, however, paint a far more extreme picture. If dark energy strengthens over time, the universe could be hurtled into an era of unprecedented acceleration. In such a scenario, every galaxy, every star, every planet could eventually be torn apart in a catastrophic big rip, where the very fabric of space-time is stretched beyond its limits. Even atoms themselves, the building blocks of matter, could be torn asunder. This is not a fanciful notion for science fiction. It is a mathematical consequence of the equations describing an accelerating universe under increasing dark energy. And unlike many cosmic events which occur in the distant future and feel abstract to us, the subtle clues that this scenario is possible are already visible in the data we collect today. The implications of a dynamic dark energy are staggering, reaching far beyond the confines of physics. The very framework that has guided cosmology for decades, the notion that the universe can be studied and understood as a predictable system, is suddenly unstable. Astronomers and physicists are being forced to grapple with a new reality, one in which the fundamental forces themselves are not fixed, but evolve over time. This challenges not only our models of galaxy formation and cosmic evolution, but our philosophical understanding of the universe. If the forces that shape reality are fluid, then the cosmos is not the steady, reliable stage we once imagined. It is a living, shifting system, unpredictable in ways we are only beginning to comprehend. Consider the consequences for the story of the universe itself. For decades, astronomers have constructed a timeline stretching from the Big Bang to the present day and beyond. This timeline has been based on the assumption that dark energy is constant, a cosmic metronome ticking steadily through eons. Now, that clock may be off. Galaxies that appear younger or older than expected, structures that formed faster than physics predicted, and deviations in the velocities of far-off cosmic objects all hint at a universe far more complex than the simplified models we once relied on. Dynamic dark energy could mean that some cosmic regions expand faster than others, that the universe's history is not uniform, and that its ultimate fate is not a single, inevitable outcome, but a spectrum of possibilities. The search for answers has become a global scientific endeavor. Teams of astronomers are studying supernovae, the exploding remnants of dying stars, because they serve as cosmic standard candles for measuring distances across the universe. By observing the brightness and redshift of these explosions, scientists can infer the rate at which the universe has expanded at different points in time. Deviations from the expected pattern may provide direct evidence that dark energy is changing. Similarly, detailed studies of the cosmic microwave background, the relic radiation from the early universe, allow physicists to map subtle variations in density and energy that could correspond to fluctuations in dark energy over time. Advanced instruments, such as the Vera Rubin Observatory, the James Webb Space Telescope, and next-generation cosmic microwave background observatories, are crucial in this research. They provide the precision necessary to detect minute variations in distant objects, enabling astronomers to test these dynamic dark energy models. The results are already tantalizing. Preliminary analyses suggest that the universe's expansion rate is not uniform across cosmic time, supporting the idea that dark energy may evolve in strength. Beyond the scientific models, this revelation carries profound implications for humanity's place in the universe. For centuries, people have looked to the cosmos for a sense of order and permanence. Even as our understanding of the solar system and galaxies has grown, we have relied on certain constants, the speed of light, the laws of gravity, the uniformity of physical forces, to provide a stable framework for comprehension. Now, the notion that dark energy itself may shift over time introduces an element of unpredictability at the very foundation of existence. It's a reminder that the universe is not merely a backdrop to human life, but an active, dynamic system, still full of mysteries. The philosophical weight of this discovery is equally profound. If the forces shaping reality are in flux, then the story of the universe is not one of inevitable progression, but of uncertainty and evolution on a cosmic scale. The notion that the universe might end not in a quiet, slow fade, but in a violent expansion that tears everything apart, challenges our assumptions about permanence and stability. It forces us to confront a reality in which even the fundamental rules we take for granted may shift without warning, and where the future is as uncertain as it is vast. Moreover, the potential variability of dark energy has practical implications for future generations of astrophysicists and cosmologists. Models of star formation, galaxy evolution, and even the distribution of matter across the cosmos may need to be rewritten. Predictions about the formation of black holes, the growth of cosmic structures, and the behavior of dark matter, all interconnected with dark energy, may require fundamental recalibration. Theoretical physics may have to integrate these fluctuations into new frameworks, perhaps redefining our understanding of space-time itself. In short, the assumption of constant dark energy, the cornerstone of modern cosmology, is being questioned at the highest levels of scientific inquiry. What was once seen as a cosmic constant, a reassuring number ensuring the universe's steady expansion, is now understood as a possible variable, a dynamic force with consequences that ripple through every aspect of the cosmos. It is a reminder of the humility required in scientific exploration. The universe is not obliged to behave in ways that satisfy human expectations. Instead, it continues to surprise us, challenging our understanding, expanding not only in space, but in the depth of mystery it holds. The work continues. Each new observation, each refined measurement adds a piece to the puzzle. But one thing is clear: the idea that the universe is a predictable, unchanging system has been upended. Dark energy, once thought to be a steady, invisible hand guiding cosmic expansion, may instead be a dynamic, evolving force. Its variability could dictate whether the universe slows, accelerates, or tears itself apart in a spectacular finale. And while humanity may be far too small to influence these cosmic outcomes, our ability to observe, measure, and understand them is a testament to the power of curiosity and intellect. Ultimately, the discovery that dark energy may not be constant forces us to reconsider not only our scientific models, but our philosophical relationship with the cosmos. We must accept that the universe is far more fluid, unpredictable, and complex than ever imagined. In embracing this uncertainty, we gain something almost as important as knowledge itself: perspective. We come to understand that our existence is part of a dynamic, evolving universe, one in which the very forces of nature are alive, shifting, and full of surprises. And as we continue to probe the depths of space, measure distant galaxies, and refine our understanding, we are reminded that the story of the cosmos is not finished. It is only beginning, and the next chapter may be far stranger and more wondrous than anything we have yet imagined. Dark energy's changing behavior could alter the fate of the universe. Here's an expanded version of your text into a detailed 600-plus word narrative, keeping it engaging, dramatic, and suitable for a script or article. If dark energy is not constant, then the very foundation of what we thought we knew about the universe's destiny may be fundamentally flawed. For decades, cosmologists have operated under the comforting assumption that dark energy is a fixed, unchanging force, a silent hand pushing the cosmos outward at a steady rate. This assumption shaped our understanding of cosmic evolution, allowing us to construct models that predicted a relatively predictable, almost serene future for the universe. The dominant scenario, known as the heat death of the universe, imagined a cosmos that would continue expanding forever, gradually cooling as stars burned out, galaxies drifted apart, and all matter dissolved into a cold, dark void. In this vision, trillions of years into the future, the universe would be a silent, frozen expanse, stable, predictable, and complete in its gradual decay. Dark energy's constancy was the guarantee that this fate would unfold exactly as expected, but the possibility that dark energy is dynamic, fluctuating in intensity over time, changes everything. If dark energy strengthens as the universe ages, the cosmic future could be far more violent than previously imagined. Rather than a slow fade into darkness, the universe could face what scientists call the Big Rip. In this scenario, accelerated expansion would continue to intensify, ultimately growing so extreme that it overpowers every other force in the cosmos. Galaxies would be torn apart, stars and planets ripped from their orbits, and eventually even atoms themselves would be disassembled as the very fabric of space-time unravels. The Big Rip represents a universe not just cooling, but actively disintegrating, a final act of cosmic violence on a scale so immense that it's almost impossible to visualize. This isn't some abstract speculation. It is a direct consequence of the mathematics governing a universe dominated by a dark energy force that grows stronger over time. On the other hand, if dark energy diminishes over time, the universe's story could take a dramatically different turn. As the repulsive force of dark energy weakens, gravity might reclaim control over the cosmos. Galaxies, star clusters, and interstellar matter could begin to slow their outward journey, eventually succumbing to gravitational collapse. In this reversed cosmic trajectory, the universe could contract into a singularity in a scenario known as the Big Crunch. Matter, once spread across billions of light-years, would be compressed back into an infinitely dense point, echoing the conditions of the Big Bang itself. Unlike the cold, slow fade predicted under constant dark energy, this outcome is explosive in reverse, suggesting a cosmic rhythm where beginnings and endings might be far more intertwined than we previously imagined. Even more fascinating and profoundly unsettling are theoretical models that propose dark energy could fluctuate cyclically, varying in strength across cosmic epochs. In such a universe, phases of rapid expansion might be followed by periods of relative stability or even contraction. Galaxies could drift apart during one era, only to converge under a temporary slowdown in another. The universe would no longer be a steady, linear progression from the Big Bang to eventual cold death. It would be a dynamic, ever-changing entity, its fate contingent on the ebb and flow of an invisible force we are only beginning to understand. Such a model transforms the cosmos from a predictable machine into a high-stakes, living drama where the ultimate destiny of stars, galaxies, and possibly life itself is uncertain, constantly shaped by forces beyond our immediate comprehension. The discovery of variable dark energy is not just an adjustment to a scientific equation, it is a paradigm shift. It forces us to abandon the comforting idea of a universe governed by immutable rules and embrace the possibility of a cosmos that evolves unpredictably, where fundamental forces themselves are in flux. The stakes are immense. Every prediction about the formation of galaxies, the behavior of black holes, the lifespan of stars, and the ultimate fate of matter must now be reconsidered. For humanity, this revelation is both humbling and inspiring. It reminds us that the universe is far more complex and dynamic than our models suggest, and that our understanding of reality is still in its infancy. In short, the discovery of dynamic dark energy turns our vision of the cosmos upside down. The universe is no longer a steady, predictable expanse, but a stage for an ever-changing, high-stakes drama. Accelerating expansion might tear apart everything, weakening energy could lead to collapse, and cyclical fluctuations could produce a cosmic rhythm beyond imagination. Each possibility carries profound implications not just for science, but for our perception of reality itself. The cosmos, it seems, is not a silent, unchanging backdrop. It is alive, evolving, and unpredictable, and the next chapter of its story may be far stranger and more dramatic than anything we have yet imagined. Studying dark energy could unlock the universe's deepest secrets. The universe is vast, mysterious, and often stranger than we dare imagine. For decades, one of the most profound puzzles in modern cosmology has been the nature of dark energy, a mysterious force that permeates space and drives the accelerated expansion of the cosmos. For nearly a century, dark energy was thought to be constant, a uniform background pressure pushing galaxies apart at a steady, predictable rate. This assumption allowed scientists to create models of the universe's evolution with a comforting degree of certainty, providing a framework to predict its long-term fate. But the story is no longer so simple. Recent research indicates that dark energy may not be a fixed force at all. Instead, it might fluctuate over time and space, shifting in ways that challenge the very foundations of physics. The variability of dark energy isn't merely an academic curiosity or a question of whether the universe will end in a cold, quiet fade or a violent big rip. It represents a doorway into the deepest questions of physics, cosmology, and even the origin of existence itself. Dark energy is intimately connected to the fabric of space-time, the subtle quantum fields that fill the universe, and the limits of general relativity as formulated by Einstein. Understanding its behavior is not just about charting the universe's expansion. It may hold the key to reconciling quantum mechanics, the physics of the very small, with gravity, the force that shapes galaxies and governs the large-scale structure of the cosmos. Recent advances in observational astronomy are providing unprecedented opportunities to track dark energy in action. High-precision surveys and telescopes are capable of mapping the positions, movements, and redshifts of millions of galaxies, spanning billions of light-years. Projects like the Dark Energy Survey, which has already collected data from hundreds of millions of galaxies, and the upcoming Euclid mission, which aims to study dark energy and dark matter in exquisite detail, are revolutionizing our ability to observe the universe's expansion. Meanwhile, the Vera Rubin Observatory, with its wide-field survey capabilities, will capture time-lapse images of the sky, allowing astronomers to monitor the motion of galaxies over decades. By comparing these observations across vast distances and timescales, scientists can begin to detect subtle variations in dark energy's strength and behavior, clues that may point to its origin, its physical nature, and its ultimate fate. The implications of these studies reach far beyond astronomy. Dark energy is not simply a force operating on the scale of galaxies. It may be intimately tied to the quantum structure of reality itself. Some theoretical models propose that dark energy arises from the vacuum of space, a seething backdrop of quantum fluctuations that never truly vanish. In this view, the universe is never empty. Even nothingness is alive with quantum activity, giving rise to energy that manifests as the cosmic push we call dark energy. If dark energy is indeed dynamic, fluctuating over time, it could offer the first observational window into these hidden quantum effects. In essence, by studying dark energy, humanity may be peering into the very machinery of reality, exploring phenomena that have remained invisible for the entire history of scientific observation. The variability of dark energy also challenges the limits of Einstein's general relativity, the theory that has successfully described the universe for more than a century. General relativity assumes a smooth, continuous space-time, governed by predictable relationships between mass, energy, and the curvature of the cosmos. But a fluctuating dark energy component introduces complexity into this model, suggesting that the forces shaping the universe may evolve over time in ways we have yet to fully understand. If confirmed, this would require a radical revision of the standard cosmological model, introducing new physics that could unify quantum mechanics and gravity, an achievement that has eluded scientists for decades. In practical terms, understanding dark energy has profound consequences for humanity's long-term future. While we often consider interstellar travel, colonization, or resource extraction on cosmic scales to be science fiction, the reality is that our survival and expansion as a species may one day depend on accurate predictions of cosmic expansion. The motion of galaxies, the density of matter across space, and the rate at which the universe expands will all influence the feasibility of reaching distant star systems, establishing self-sustaining colonies, or harnessing resources beyond the solar system. If dark energy grows stronger over time, accelerating expansion could isolate galaxies from one another, making intergalactic travel impossible. Conversely, if dark energy weakens, the universe may slow its expansion, creating different strategic possibilities for long-term exploration and settlement. The stakes are no longer abstract. They touch on the survival of life in a universe governed by forces far larger and stranger than earthbound physics can fully account for. Observational data is beginning to provide tantalizing hints about the complexity of dark energy. Certain distant galaxies appear to be moving slightly faster or slower than predicted by models assuming constant dark energy. These variations, though subtle, are statistically significant across billions of light-years of cosmic history. Researchers are beginning to map these fluctuations, identifying patterns that may suggest dark energy is influenced by cosmic structures or quantum effects. The very idea that dark energy could vary spatially or temporally opens new questions about the universe's evolution. Could there be regions of space where dark energy is weaker, allowing matter to coalesce more efficiently? Could there be epochs in cosmic history where its strength oscillates, altering the rate at which galaxies form or clusters grow? These questions strike at the heart of cosmology, challenging long-held assumptions and inviting a new era of scientific discovery. In addition to its cosmic and philosophical significance, the study of dark energy could have unexpected implications for fundamental physics. Many theories suggest that the universe operates on principles that connect the largest scales, entire galaxies, and the observable universe itself, with the smallest subatomic scales governed by quantum mechanics. If dark energy fluctuates, it may be a macroscopic manifestation of microscopic processes, a link between quantum fields and cosmic evolution. Detecting such a link would be one of the most significant breakthroughs in physics.